Chapter 10. Chapter 10 is about phase change. Now, what is phase change? So, whenever you have ice and it melts, it changes to liquid water. So, it's changing phase from a solid to liquid. And when you boil that water, it changes to steam. So, it changed its phase from a liquid to a gas, which is steam. So, whenever you have phase change, a fluid reaches its saturation temperature. So everyone knows that the boiling point of water is 100 degrees Celsius. So that's the saturation temperature at which the water will start boiling. And then until the entire water has boiled, it will remain at that constant temperature while the heat is being added to it. And if you are freezing the water and converting it to ice, the water slash ice will remain at that particular temperature until the entire mass of water is converted to ice while the heat is being removed from that particular system. So in phase change, you have your phase being changed at a saturation temperature, and that temperature remains constant. So this is our equation for the heat rate. There is some heat transfer coefficient associated with it, and you will have some contact area between your phase and the surface, and the temperature difference will be between the saturation temperature of the fluid and the surface temperature in which the fluid is in contact with. So the TS here is the saturation temperature or the phase change temperature, like I just explained. So let's look at what is called as condensation rate. So whenever you have water vapor or steam, and you have steam, say, blowing or moving over a cold plate, so you will have condensation on that plate, and that condensation is quantified by a condensation rate. And the condensation rate is nothing but how much water is being added to that plate, or how much water is being changed from steam to the liquid, from gaseous phase to the liquid phase. So it's denoted by m dot, and this m dot is can be written as the heat rate divided by a coefficient, which is the corrected heat of fusion, a corrected heat of fusion. Okay, so our Q, as we mentioned here, is some heat transfer coefficient times the area into the temperature difference between the saturation and the surface temperature divided by the corrected heat of fusion. Okay, so in thermodynamics, we know that our energy stored is a combination of internal energy, kinetic energy, and potential energy. But for our course, we ignore kinetic and potential energy, and our internal energy can be written in a form of sensible heat and latent heat. So what is sensible heat and latent heat? Sensible heat or sensible energy is responsible for change in temperature. So whenever you have water and you start boiling tap water at room temperature, your the temperature of water increases. That increase is due to the sensible heat. But once you reach the saturation temperature and your water starts to boil, your water is now at a constant temperature. Now that doesn't mean that you don't have a change in energy, or you don't have any internal energy that's being changed. You do have internal energy, but it's in the form of latent energy, which is responsible to change the phase of that particular material. So sensible energy is responsible for phase change, for changing the temperature, and latent energy is responsible for changing the phase. So now let's look at an important concept in this chapter, which is pool boiling. So whenever you have, whenever you have water and you're boiling it on a burner or on a stove, your water is at rest. As you start applying heat to the water through pan or through induction, your say you're boiling it in a saucepan, your saucepan will start heating up, which will eventually create a convective current, or which will create motion of that particular water uh, free convection, and so the boiling due to free convection, it's like mostly boiling is due to free convection. There are scenarios in which you will have boiling or phase change which occurs due to forced convection as well. We'll look at that in some time. So when you have boiling due to free convection, it's known as pool boiling mostly. So pool, so there are different modes of boiling, or there are different types of boiling that happen as you are in different phases of temperatures and heat fluxes. So let's look at figure 10.4 here, which I've taken from your textbook. The x-axis here is the excess temperature. So it's the temperature difference between your surface temperature and the saturation temperature, and the y-axis here is the heat flux. Okay, so region 1 is called as free convection, where you have temperature rising linearly with your heat flux. So you will have basically, this is representing your Newton's law of cooling, where your heat flux will be h times delta T. So it will be h times this delta T E right here. Okay, so you have a linear increase up to the point A. So when uh, when you reach point A, okay, so when you reach point A, that's when you are in the nucleate region. This means you have bubbles being formed in your water. If you're boiling, let's say you're boiling water, so you have a bubble formation that takes place, and uh, these bubbles will be isolated bubbles. So you will have like distinct bubbles that you will see between A to B, and when you cross the B point, you will and as you add more heat to the system, so this means that as you increase as you increase your delta T beyond the point B, beyond point B, there will be more nucleation sites. Now what that means is that there will be more locations where you will have bubble forming, and this will allow the bubbles to merge and form into jets. So uh, and remember one thing, that the bubbles that are forming are not air bubbles. The bubbles are water vapor, will be the bubbles of the same material that you are boiling. So in this case, the bubbles will be made up of water vapor. So when you're in the region between B and C, these you will have more sites, or more nucleation sites, more sites where bubble formation is occurring, which will which means that the bubbles will interfere, and there will be coalescence that will be taking place, and the vapor will just escape through jets or columns, which which will happen due to the merging of these bubbles. So you will have something like you see in figure A here. So because there are multiple sites where bubbles are being created, these bubbles just merge, and you have uh, water vapor escaping through jets or through columns, and you don't see distinct bubbles being created here. So this is what happens when you go beyond point B. Now as you move beyond C, or when you are at C, the C point here is known as the critical heat flux. So the critical heat flux is the point where you will have maximum boiling, or maximum boiling bubble formation. And beyond this point, as you start adding heat, or if you go beyond this point, there is a decline in heat flux, and that's because your convective coefficient will start decreasing. Now what happens is that as you add more heat, or as you go beyond this point, beyond the critical heat flux point, there will be a film of vapor that will be created on the surface because of the rapid boiling or because of the additional heat. Now what this film of vapor will do is that it will blanket the surface and it will cut the contact between the surface and the water. So uh, so basically that you don't so basically the film of vapor that's created, uh, it will create a blanket of the vapor of its so blanket of water vapor between the liquid and the surface. Now we know that the thermal conductivity of any gas is smaller than thermal conductivity of vapor. So that means that the heat being transferred through the gaseous phase will be much lower than what it will be the heat being transferred through a liquid phase. Now because you have a smaller contact between your liquid and the surface of the say metal over which you are adding heat, uh, you have the curve going down, and it goes down until you hit the Leiden-Frost point. Now the Leiden-Frost point is gives you the Q minimum. So until this point you have unstable boiling, or it's also called as a transition boiling or a partial film boiling, which occurs, and that's because you don't have the blanket over the entire surface but only in partial areas of the surface which is adding heat over to the liquid. Now at point D, or at the Leiden-Frost point, the now the surface is completely covered by a vapor blanket, and now the heat is being transferred from the surface of the metal to the liquid just by conduction and radiation and not by convection. So that's why you have a very small amount of heat flux being added to the liquid at this point here, and this was first recognized by Leiden-Frost, and that's why it's named after him, after Leiden-Frost. But as you increase the delta TE beyond this point, the uh, surface temperature of the metal will increase, and the radiation effect will be dominant. So now in in the transition region, you have heat being transferred due to conduction and radiation, where radiation wasn't that dominant. But as you go beyond point D, you have heat transfer due to radiation that is a dominant mode. So uh, as you go beyond point D, you have something which is called as a film boiling. Now, why it is called film boiling? Because you have a film of water vapor that is covering the entire surface, and it is obstructing, or it cuts the contact between the liquid and the surface, which is providing heat to the liquid. Now, as the surface temperature increases, the heat flux also increases, because now there's heat being transferred due to radiation, and we can see in this figure B right here, that there's a film of water vapor that's being created, and uh, the number of and the bubbles, or the boiling rate, is different from what we had in A. And if you see the x-axis on the graph right here, this might so your temperatures in the vapor phase or in that blanket may go as high as 1000 degrees Celsius, and it's called a boiling crisis because this might be uh, So it's 1,000 degrees Celsius, and this might be the point where your metals start to melt. So if you are doing it in a say an iron pan, your iron may start to melt, and uh, you may damage your pan. Or if you're doing it in a coffee maker, if you're boiling water in a coffee machine, your coffee machine uh, may just break. So that's why this point is called this region here is called boiling crisis. And if you have a coffee maker, if this point is reached, it will just cut off uh, the supply and turn off your machine. Okay, so now let's look at nucleate boiling. Now we've seen that the this is the relation for nucleate boiling. This is a general formula for Nusselt number, which is some constant times Reynolds number to the power m times Prandtl number to the power n. And the Fc here, I'll just explain what the Fc here is. Now what happens in nucleate boiling is that you have bubbles being created from the surface. Now as these bubbles rise, these bubbles create a flow inside that liquid. Now we can say that the bubbles are responsible for creating or for generating the flow inside that liquid, and bubbles are an external agent. So we can assume that this is an example of a forced convection. So because of the bubble formation, there is some fluid motion that's taking place in the fluid. And if we have fluid motion due to an external agent, we can characterize it as a forced convection. And that's why we have these FCs in the subscripts here, which actually represent forced convection. Now let's move on. Now let's move on and let's look at the appropriate length scale which we must consider for such problems. And in this problem, in for boiling problems, we look at the diameter of the bubble. So dB here is the bubble diameter, and it's proportional to sigma under root of sigma by g times rho of L minus V. So sigma here is the surface tension of the liquid, rho L is the density of the liquid, and rho V is the density of the vapor phase. Now where did we get this relation from, or this proportionality from? This is by equating or by doing a force balance on the bubble. So we can balance, so we know that the buoyancy force on the bubble will be equal to the surface tension force, and by doing that force balance we can say that the diameter of the bubble will be proportional to the square root of surface tension divided by the gravity times the difference in densities. Now we can associate we can also define another term which is called as the bubble velocity or a characteristic velocity. So let's say this is the characteristic velocity, and it is proportional to dB by TB. Now the temperature that you see here, oh sorry, the time that you see here is the time between the between consecutive bubble formations. So the time TB is equal to the energy it takes to form a vapor bubble uh, divided by the rate at which heat is added over the solid vapor in contact. So in other words, let's say this is a surface that you have, and you are this is it's you have bubble formation on the surface. So as soon as you have a bubble that's leaving the surface, you will have a bubble that will be generated, that will start generating on the surface, and the difference and this the time difference between the two bubble formation is nothing but TB, and TB is equal to rho time HFG cube of the bubble divided by the heat flux time dB square. Okay, now substituting this here, our dBs cancel out and we get our characteristic velocity proportional to heat flux divided by the density of liquid times the heat of fusion. Okay, so this is another relation that we use to characterize nucleate boiling in a particular for a particular liquid. Now what this equation tells us is that if you are adding if you have a higher heat flux or if you're adding more heat to the system, that means that your bubble formation will be at a higher rate. That means you'll have bubbles forming more frequently. If you have a liquid which is less dense, that means let's say you have methanol instead of water, your bubble formation in methanol will be at a higher rate because it has a lower density. So you will have a bubble formation at a higher rate, and same relation would be true for the HFG as well. So that's why we have defined this characteristic velocity so that we understand how bubble or how frequently or how fast the bubble formation is taking place and how it is related to the bubble diameter. We we have seen that beyond the Leidenfrost point, a continuous film blankets the surface and cuts the contact between liquid and the surface. So in that case, we defined a corrected heat of fusion, which is equal to the HFG plus 0.8 times Cp multiplied by the temperature difference between the surface and the saturation temperature of the fluid. Now we can find the HFG from the table. Now we've seen that the radiation across the film becomes significant as we move beyond the Leidenfrost point, and the correlation for finding out the heat transfer coefficient is not a simple algebraic expression. So your uh, heat transfer coefficient will be a combination of convective heat transfer coefficient and a radiative heat transfer coefficient, but you'll see that it's not a simple addition and you cannot write your H in form of H convection and H radiation because you have 4/3 of the power here and 1/3 power here. So this type of equation is called as a transcendental equation, where you can't simply express it as a simple algebraic expression. Now, in such case, if you have convection that's larger than radiation, there's a simpler form of H that you can use, which is H convection plus 3/4 of H radiation. But if you have your but if your radiation, and in this case or in any case, your H radiation can be calculated as epsilon times sigma into Ts to the power 4 minus T saturation to the power 4 divided by Ts minus T saturation. So it's important to note how H changes is a combination of convection and radiation, and also you must note how we calculate the H for radiation in this case.